Hello everyone, this is Haibin. I'm gonna introduce the theoretical framework of our paper Manifold Matching via Deep Metric Learning for Generative Modeling. Later, my collaborator Mengyu would introduce the implementation details. We named the proposed framework as MVM, which means Manifold Matching via Metric Learning. Basically, it offers a geometric point of view of generative adversarial learning. First, we show the main differences between MVM and classical GANs. Classical GANs are mostly from the statistical point of view. Their networks match means, moments, etc. by measuring statistical discrepancies with respect to the underlying Euclidean distance. However, MVM is based on a geometric point of view. Its networks match centroids, p-diameters, etc. with respect to some learned intrinsic metrics. In classical GAN, two networks compete on a single min-max value function. But in MVM, we have distinct objective functions for each network. MVM consists of a distribution generator and a metric generator. We assume that the real dataset is a manifold embedded in some high-dimensional Euclidean space Rd. The distribution generator would produce a distribution measure on Rd to be the push-forward of some Fourier distribution on Rm. On the other hand, the metric generator would reproduce a metric on Rd to be the pullback of the Euclidean metric on Rn. Overall, we have a metric measure space. During the training process, the distribution generator implements manifold matching, which pulls together the real samples and the fixed samples. However, the metric generator implements metric learning using triplet loss and pushes away fixed samples from the real samples. This cartoon example depicts the training process where the fixed samples gradually converge to the real data manifold, while the real data manifold itself becomes more and more uniformly curved under the learned metric.
Hi, this is Mengyu. For implementation of triplet metric learning, we take a random batch of real data as anchor samples and shuffle the data in batch as positive samples. The generated data are used as negative samples. The learned metric is then used for matching geometric descriptors of real and fake datasets. During training, we iterate the two steps until converge. In experiments, we studied some characteristics of MVM using unconditional generation task. We found matching both centroids and two diameters provided better results than matching individual descriptor only. We also found the method is robust to batch size. We further detect the shape of real dataset by looking at the first 10 eigenvalues of distance matrix of real data samples. Figure 5 shows the shape of real datasets becomes more and more uniform during training. We evaluate results on two benchmark datasets and show performance gain compared with classic GAN objectives using ResNet generator. We further conducted experiments on LSU and Church and FFHQ datasets using a StyleGAN2 data generator. Results indicate MVM objective can also be used for generating larger images. We also conducted experiments on single image super resolution task as an example of the usage of MVM in a supervised fashion. We discussed two cases where we use MVM as a substitute of GAN loss or perceptual loss, and presented evaluation results in the two tables. Thank you for listening to our presentation. Please refer to the paper and code for more details.